Okay, good day class. Alright, so today we will start another approximation method, which is Newton-Raphson method. Alright, so before this we have learned how to use iterative method to find the approximate roots of an equation. Right, so today we will see the second method, which is Newton-Raphson method. Alright, 6.1.4. Approximation of roots of an equation using the Newton-Raphson method. Alright, the Newton-Raphson method is based on the idea of using tangent lines. Alright, we are using tangent lines to replace the graph of y equals fx near the point where f is 0. Okay, you can refer to your textbook page 179, which is something like this. Alright, so later we'll go into details how to get this diagram. Alright, so to get the formula, alright, to get the formula by using this Newton-Raphson method, to find the approximation roots, so we are going to use tangent, right? So let's refer to this diagram. Alright, we are going to explain step by step. Okay, so let's say this is a graph y equals fx. Alright, this is a graph y equals fx, and this is the root alpha. This is the root of the equation fx equals 0. When the graph y equals fx cut the x-axis at alpha, so we call this the root of equation fx equals 0. Okay, so we will choose one approximate value of x. Alright, let's say x0 lah, or you use x1. x0 or x1 both can. Or okay, so we start with x1. So let's say we choose a value of x, the initial value of x, which is close to the actual root alpha. Alright, so then we draw from x1 to meet the graph. We draw the line x equals x1 to meet the graph, let's say at point P. Therefore, the coordinates of point P will be x1 and fx1. Means sub x1 into your function. Okay, so this is your fx1, right? Then, as we say, we are going to use tangent, right? Therefore, the next step is we are going to draw a tangent at point P. Alright, so at point P, so let's say this is a tangent. Alright, so we draw a tangent at point P and extend the tangent to meet the x-axis here. Alright, so you see, this is the tangent at point P. So we draw this tangent and meet the x-axis at this point. So this is, let's say we name it x2. Alright, so you can see that x2 is very clear, is closer to the actual root, right? This is what we are going to do by using the tangent. Alright, so the next step is, since we already got our x2, so we draw a line x equals x2 and meet the curve again. Alright, so here, so let's say we name this point as point Q. Alright, with coordinate x2 and fx2. Okay, so this is x2. So here is fx2. Alright, then next we repeat the same steps. Alright, which is we are going to draw a tangent at point Q. See, we are going to draw a tangent at point Q and extend it. So you see this tangent at point Q cut the x-axis again here. Let's name this point as x3. So from here you see that from the initial value of x that we choose, after we draw the tangent, we get a value of x which is closer to the root. Alright, then from the second value, we get the point and draw another tangent. And you see that this tangent will cut the x-axis again at x3. So you see that this tangent is actually closer and closer and closer to alpha. See that? So if you repeat the same step, alright, so maybe we try one more. Let's say if we repeat the same step, Okay, so from x3 we draw a line to meet the curve again. Okay, let's say we name this point T, which is x3, fx3, right? Then at this point, we draw the tangent at point T. See or not? We draw a tangent at point T here. So you see or not? This tangent at point T, alright, cut the x-axis at here, which is even closer to the actual roots. Alright? This is a concept that we are going to use. Okay? So, you see that from the notes, So we say that we let the root be alpha, then we take x1, x our first initial, draw the tangent, alright, and the tangent cut the x-axis at x2. So from x2, we get a point on the curve and draw another tangent. Then you see that the value of x that we get will be closer and closer to the root. Alright, these are the steps that we are going to, that we have done from step 1 to step 4. Okay, this is the concept. Okay, now is how we are going to get the formula. Okay, how we are going to get the formula from the initial value of x that we choose, alright, and then closer and closer to the actual roots. How we get x2 and how we get x3 by using this Raphson method. Alright, so very simple. The step is like this. Okay? So just now we already said from x1 we get x2, from x2 we get x3, and so on. Alright, so let's say at xn, at one of the value here at xn, so the coordinate will be xn fxn, right? Just like this one. At x1 the coordinate is x1 fx1. At x2 the coordinate of the point is x2 fx2. So at x3 the coordinates are x3 and fx3, right? So at any point in here, xn, let's say, so the coordinate is xn fxn, and we know that the gradient of the tangent is f prime xn. To calculate the tangent of this, to calculate the gradient of the tangent of all these three tangents, is we differentiate the function, right? dy dx. We differentiate the function, which is f prime x, and we sub in the value of x inside the f prime x to get the gradient of the tangent, right? Therefore, the equation of the tangent, so the formula actually get from the equation of all this tangent. Alright, so by using this, remember the coordinate you have learned in Sem 1, alright? The equation of the tangent, which is a straight line, is y minus y1 equals mx minus x1. Alright, since at xn this is the coordinate, so we sub the x coordinate and the y coordinate into the formula. So become y minus fxn, m gradient is f prime xn, and then x minus x coordinate is xn. Alright, so sub the x coordinate, y coordinate, and the gradient of the tangent at this point, okay, into the formula. So we get this. Okay, and we know that each tangent line will cut the x-axis, right? Will cut the x-axis. So the tangent will cut the x-axis at x equals xn plus 1. And then y equals 0, right? For example, this is x1. So at point x1, the tangent cut at x2. So this is n plus 1, 1 plus 1, right? And the tangent at x2 here will cut the x-axis again at x3. Just now x2. So we get the tangent and cut it at x3. Right? So each tangent will cut the x-axis at the point x equals xn plus 1. If this is 1, then this is 2. If this is 2, then this is 3. Alright? N plus 1. And y definitely equals 0 because it's cut the x-axis. So we sub these two into the formula that we get here. So y will become 0, x will become xn plus 1. Yes, then we rearrange it, we will get the formula. Alright, so first step, we shift the f prime xn to the left hand side, become like this. Oh, don't forget the negative, huh? So here will become this. Then next, we shift minus xn to this side. So become positive xn. Therefore, this is the formula to get the next approximation of x. So xn plus 1 will be xn minus f xn over f prime xn. So please memorize this formula. Alright, so just now let's say we already have x1. So when we sub in x1 here, where n is 1, right? x1, x1, x1. Then when you sub and calculate all this, then you will get 1 plus 1 is 2. You will get this value without using the graph. Alright, then when you sub your x2 into the formula, so x2, 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 n is 2, right? Then you will get 2 plus 1, x3. See, so this is the formula by using Newton-Raphson method to find a series of the approximations of the value of x. Okay, so next, so after we know about this formula, so all this already stated in the notes. Alright, already stated in the notes. You can go through it. Alright, then this formula will be used continuously to generate the next approximate value of x until we are close to the root to stop. Alright, so where and when to stop? So we normally stop when A, the question asks us to stop at certain approximate value of x. For example, find until x3. Then you just stop there. Alright, or we get 2 consecutive same answers correct to certain accuracy. Okay, so the when to stop and where to stop is actually similarly to iterative method. Iterative method, same. Alright, same. Okay, then when we use an approximate value of x to generate the next approximate value of x, make sure we use a value with more decimal places, right? Same as iterative that we have mentioned, which is 2 decimal places or 2 significant figures more than the accuracy required by the question. If the question wants you to express the answer in 3 decimal places, then in your calculation, you use at least 5 decimal places. Same concept. Alright? Then, to determine the first approximate x0, like this one, x1. If the question not given, how we are going to determine what value we are going to use? Okay, we can use this method. Alright, so remember this one we have done in front, beginning of the chapter. We sub 2 integer x equals a and x equals b into the function. If the sign of fa and fb are different, remember? Then it shows that at least one of the root must lie between a and b. If y equals fx is continuous, then the value of x with the image closer to 0 will be the first approximation x0 that we are going to use. Alright, okay, let's see one example. Let's say this is a function fx, which is x plus ex. Alright, so we try 2 integers, -1 and 0. So when we sub -1 into the function, so it becomes -1 plus e power -1. So when you press your calculator, hold on, okay, I have calculated. Okay, when you press the calculator, you get -0.6321. Alright, then when you sub 0 into the function, so it becomes 0 plus e power 0, which is 1. Alright, so your conclusion will be, since fa and fb have different sign, right? One negative, one positive. Alright, then it shows that there is at least one root lies between -1 and 0. Okay, which one to use? Which one to use to start as our x1? So we see which image closer to 0. This one is 1 unit from 0. This one is 0.6 unit from 0. So this is closer to 0, right? This is closer to 0. Therefore, we will choose our first approximate value of x that should be used, alright, in our calculation into the Newton-Raphson formula. Will be -1. We choose this one because give me the image even closer to sorry, even closer to 0. All right, this is how we choose. Actually, similarly to iterative method. All right, this is a concept. All right, before we go to more example or exercise, we have to know about one thing, which is the rate of convergence. For Newton-Raphson method, we have to consider this. For iterative method, we have to see the modulus of G prime x, right? So for Newton-Raphson method, we have to check the rate of convergency. What this means? Okay, this one means the success of the Newton-Raphson method. So means that Newton-Raphson method not necessarily every time success. It depends on two important criteria. All right, one, the initial approximation that we choose. All right, if the initial approximation is too far from the root or beyond a turning point, then Newton-Raphson method will be failed. It means that you cannot use Newton-Raphson method to get a set or a series of approximation value of x that closer and closer to the root that we want. It will go further and further. All right, so first, the initial approximation. Second criteria will be the value of f prime x is equal to 0 or too small. Means the tangent at certain point. The tangent at certain point. The gradient of f prime x, the value of f prime x is equal to 0. Equal to 0 means what? It's a horizontal line, right? Or too small means almost close to a horizontal line. This one also cannot. It will make Newton-Raphson method fail. Okay? So let's see the example. What does these two means? Okay, you can refer to your textbook, page 180. There is one example to show this failure. Okay, this one. Okay, so the first one is this example. This is the root that we want. Of course, you see this diagram, you know we have two roots. But let's say this is the root that we want to calculate. All right, so the turning point is here. But the first initial value of x that we choose is here. See that? Oh no, sorry. Here, sorry. Here. Okay, so this is the actual root that we want to calculate. And we choose the first approximate value is here. 1 is too far. It's too far from the root that we want. All right. Second is beyond a turning point. You see, this is a root. This is a turning point. But the first approximation that we use is here, which is already over a turning point. These two criteria. All right, makes this Newton-Raphson method fail. Okay, what failed? You see, this is at naught, right? We choose a point here, then we draw a tangent. So you see the tangent cut the x-axis again here. This is the next approximate value of x that we got. And it is actually further and further from the actual root. See that? Okay, so this is the meaning of the first criteria. And the second criteria is the f prime x is equal to 0 or too small. The second example, next page. All right, here. Which the f prime x equals to 0 or is too small. Means that the tangent that we draw is horizontal, almost horizontal. Okay, let's say this is the actual root that we want to calculate. All right, and this is the first approximation that we choose, the initial approximation of x that we choose. All right, you see at this point, this is a tangent. This tangent is too small. You see this tangent is almost close to horizontal already. So what happened? So when we draw the tangent at this point, and we extend and meet the x-axis again, you see, the next approximation we get is here, which is far from the actual root. The first one even closer. But when we draw the tangent, the next approximation that we get even further from the actual root. All right? Okay. So this is the two criteria where will make this Newton-Raphson method fail. So remember these two. Okay, then next. So just now we already discuss about these two criteria. You have to memorize it. The question might ask, okay, in STPM. Thus, Newton-Raphson method works best if the initial approximation is sufficiently close to the root. Alright? Then, next. Alright, so possible reason why the Newton-Raphson method may fail to converge. Converge means to get a series of approximation value of x which is closer and closer to the actual root. Included, we written all 5 here lah. Okay, but remember the most important is this one and this one. Alright, so A, as we said just now, the first approximation is too far from the root. Okay. B, the first and subsequent approximation cause the function to become undefined. Means you get 1 over 0, something like that. C, the gradient of the curve is very small or 0 near an estimate. And number 4, the rate of change of the gradient near the root is too great. Rate of change of the gradient means the gradient change, let's say at the initial like this. Then suddenly the next become very horizontal already. This is the meaning. Alright. And the last one, there is a turning point between the root and the estimate. A and E are the first example that we discussed in the textbook just now. Okay. So these are the reasons why the Newton-Raphson method may fail. Okay. Memorize this. Alright. So we will discuss a few examples in your textbook. Alright, we will discuss examples 6, 7, 8, 9 in page 181. So exercise 6.2 will be your homework. Alright, exercise 6.2 will be your homework. Then we will discuss a few past year questions. So from here you can see actually Newton-Raphson method is quite popular in STPM. So you see we have 1, 2, 3, 4. Some more, the next page. Alright. Here until here. It's quite popular question in STPM, Newton-Raphson method. Alright, and there will be some more question in STPM 2018 repeat paper until 2020 repeat paper. Alright, so means many lah. So you have to check. Okay, so let's see the example first. Some example in your textbook. What are the steps that we should use or write when we answer the question? Okay, so please practice the correct and actual step. Okay, don't simply write answer only like that. Okay. Alright. Okay, example 6. So the question is like this. Show that the equation x plus ex equals 0 has only one real root and find its value correct to 3 decimal places. Alright, so remember, to show only one real root, we need graph. Alright, so we split the left hand side into 2 parts, ex and minus x, which are the 2 graphs that we can sketch easily. Alright, so this is y equals ex, this is the line y equals negative x. Alright, so after you sketch a graph, don't forget to write your conclusion. So the sketch show that there is only one point of intersection, alright, here. And so the equation x plus ex equals 0 has only one real root. Okay? Then which root we are going to choose? Remember the example that we discussed just now? Here. See here. You remember this one? It's actually the same here. Just now, to show there is only one real root, we need the graph to show only one intersection point. Okay, then where is the root? We cannot approximate the root from the sketching, remember? Then we can calculate, we can do this. Remember just now? We show f0 and f negative 1. And there is opposite sign. So we know that the roots actually lies between 0 and negative 1. Alright? So just now we already say, right, we will choose the value which is closer to 0. So we choose this one. This is closer to 0, so we choose x equals negative 1. But between 0 and negative 1, I think negative 0.5 will be even closer. Will be even closer. Therefore, this example, they choose the first approximation, x equals negative 0.5. Alright? So remember, this step is to show us where the root lies between. So the root lies between 0 and -1. And what we are going to choose as our first approximation is up to us, as long as any value between 0 to -1. Alright? Okay? So in this example, they choose the first approximation is -0.5. Okay? Then, see, we left the left hand side as fx. Then we differentiate it. We need differentiation now. Remember, Newton-Raphson method. In the formula there is differentiation now. Fx over f prime x. All right. So take x naught as -0.5. Sub -0.5 into your formula of the Newton-Raphson method. Okay, this formula. Remember, sub inside this formula. So this is x naught, so this is x1. Therefore, x1 is -0.5 minus, to find this means sub x naught into your f, this one. Oh, don't sub wrongly, yeah? The numerator is function, the denominator is the differential equation, alright? So sub x naught into your fx, so -0.5 plus e to the power of -0.5. Okay, then numerator, you sub -0.5 into your f prime x, so 1 plus e, -0.5. You still remember how to differentiate this one, differentiate x, you get 1, differentiate ex is still ex. Alright, show this one, show this step, very important. Show the step you sub the value into the formula, incomplete. Alright, then you press the calculator, you get this answer. Alright, so for this step, you actually again can use the, remember your calculator, you can use the equation format. Alright, remember, press the alpha. Hold on, okay, let's see. Okay, x, can you see, okay, x minus, right, fx, so your fx is x plus ex, bracket, alpha again, x, plus, this is the e, okay, e power, also another x, see that? Then close your bracket, alright, then equal. See that? Press the function, press the fraction button. Then below here is f prime x, so your f prime x just now is 1 plus ex. So 1 plus, you can see e is this button here. E, the power is x. So wherever you want to press x, you have to press the pink color alpha and choose the x. See that? You can set this formula into your calculator. Alright, then each time you just press calculate. Remember the button calculate, press calculate. They ask you what is the x that you want to use. So just now the first approximate is -0.5. See? -0.5. See? Okay, press my calculator. I have to press twice. Yes, you see? Come out -0.5663. By right, the question 3 decimal places, you should use 5 decimal places but the example here use 4, then never mind, we just follow 4. But in your exercise or when during exam, please write 2 decimal places more. Okay, can see so this is how you can use your calculator. Alright, so you get the next x is -0.5663. Okay, then next step is can see. Okay, so sub again the value that you calculate just now into the formula again. You see, remember, just same like iterative method, at least twice, show at least twice you sub all the value incomplete like this. Okay, so after you write, then again just press your calculator. Just now you got right. Remember, every time must press the button calculate. Then that asks you what is the x that you want to use. So it's -0.5663, right, just now. Okay, so equal. See that? They come up the question, the answer, negative 0.5671. All right? 0.5671. Okay? So remember, show this step at least twice, 2 times. Okay, the next one is actually you can just press your calculator for the answer. Press. Just now the answer is negative 0.5671. Negative 0.5671. All right, can see? Yes, equal. Yeah, you get almost similar answer already. Negative 0.5671. So for the third one, you can skip this and just write the answer for the following. But this step, please at least show twice. Okay? So we get 2 consecutive answers which are the same. Therefore, we can stop here. Then write conclusion. Every time, please write the conclusion and the final answer. Hence, the approximate root is negative 0.567. Correct to 3 decimal places. Please write. If you don't want to write in sentence, bracket 3dp. Alright? Must write. Okay? So this is the complete method or complete ways for you to answer in exam. Okay? Alright, next example. Bigger. Okay, example 7. Show that this equation has a root between 2 and 3. So to show equation, we just need to sub 2 and 3. And you see opposite sign. Must write conclusion. F2 and F3 have opposite signs, so there is a root between 2 and 3. Alright? Then use the Newton-Raphson method, and with this initial value of x, alright, determine by means of 2 iteration and approximation to this root, given your answer to 2 decimal places. Alright? 2 iteration means they only want you to show another 2 answers. This is what I mean just now, remember? Where to stop? First is, like just now, we get 2 consecutive answers which are the same. Then we can stop. Next is follow the question. The question only want 2 iterations, means they only want you to show another 2 more answers. Okay? So fx, remember to differentiate them. F prime x, to show there is a root between 2 and 3, we calculate. So you see that the root, this one is closer to 0 compared to 13, right? This is closer to 0. Alright, therefore they choose approximate root which is closer to 3. See, 2.8. That's same lah. This is the F1. Sub everything here into the formula. Get the answer. Then second. Excuse me. So because the question want 2 decimal places. So that in the example you see they convert to 3. But doesn't matter lah. Because this question they actually just want you to show 2 more iteration. So you just need to calculate your x2 and x3. Then you can stop. Alright? Can I? So let's see one more example which is slightly different compared to what we have done. Okay, this question sounds like this. If A1 is the first approximation to a root of this equation, where B is given, then show by using Newton-Raphson method that there is a second approximation given by this. Alright, then A, use this result, find 2 further approximation to 2 to the power of 1 over 4 by taking A1 equals 1 as first approximation, then give your result in appropriate decimal places. Next, sketch the graph and show the geometry relation between the approximation on the curve. See, would you expect the next approximation to be smaller or greater than the value of 2 to the power of 1 over 4? Give reason for your answer. Alright, so you see this is quite good question where they really test you about the concept of Newton-Raphson method. Alright, let's see the solution. Here. How to get this? They ask us to show, right? So very simple. You are asking to solve this equation, right? So they just rearrange this one only actually. They just move the B to the left hand side and make the right hand side 0. Okay? Therefore you get this. So let this one become So just now, after we rearrange, you actually get this equation. So let the left-hand side become your fx. So differentiate them. Then let the first approximation A1, right? So use Newton-Raphson method. If first approximation is A1, by using the Newton-Raphson method, we can calculate A2. So means we sub A1 into the function. Alright, so FA1 means sub A1 here. So you get this. F prime A1 means sub A1 into your F prime X. So you get this. Alright, so the next step is they split this one into two fractions. A4 over A3, so left 1. Then B over 4. Okay? Then they combine them. Or they combine these two because A1 and A1. Or they combine this one. So this is 4A1 over 4. Okay? This is 4A1 over 4. So 4A1 minus 1A1, 3A1. So this is what the question wants us to show. Okay? So we have answered the first part. Okay, second part, they want you to use this formula, okay, to calculate or to solve this thing. X equals 2 to the power of 1 over 4. Alright, so you see this is fraction root. So we make both sides to the power of 4. So to the power of 4, so you get this thing. So when you compare this one to what you have done here, compare this one to what you have done here, it's actually same. Means that your B is 2. See that? So your B is 2. Okay? So from here we determine the value of B. Then the first approximate A1 is 1. So second, this is second, right? Sub your A1, which is 1, and sub your B, which is 2, into the formula, into this formula. Alright? So you get 1.25. Okay, sub 1.25 again into the same formula. Alright, into the same formula, you get 1.1935. Alright, so just now the question said get another 2 more answers. Then you can stop here. That's it. Alright, okay, part B. Alright, so part B, what the question asked just now. You see, they want you to sketch this graph. Alright, and show the geometry relation between the approximate root. So you see, this is how you can sketch the graph. Alright? It's just a graph like this. It's like quadratic graph. It's actually a quadratic graph. Same like your x squared. It's a quadratic graph when x0, y equals -2 here. Okay, it's a quadratic graph. So just now we know that the root lies between, just now the root lies, the actual root, you see 1.25, 1.19. So it's from 1 to 1.25. Alright, so they just want you to sketch the diagram to show how to get the next approximate value. Alright, we start from 2, remember? Just now this is 1. We start from 2 here. From 2 we get the point. Then we get the next one is, sorry. We start from 1 here. The first approximation is, sorry, can see. The first approximation is 1. Okay, means we start from 1. Alright, we start from 1 here. This is the first approximation. Then we draw the tangent. Alright, and we get the next is 1.25. Okay, can see. The next one is 1.25 here. Okay, from here we draw another tangent. Okay, so the tangent come here, which is 1.1935. So you see that from here, it come here, then you see the next one is actually closer and closer and closer to the actual root. Alright, this is what they want you to show. They want you to show the concept, how to use the tangent to get the approximate value of x. Alright, okay, so the last part is, would you expect the next approximation is smaller or greater than the value of 2 to the power of 1 over 4? Remember our the value of x that we are calculating is to solve this equation. Alright, so they ask and then answer y. So this is how they answer. So from the graph, from this graph, it is observed that the tangent at point x equals a2, which is here, alright, a3, a4, approach tangent at x equals 2 to the power of 4 from the right, from here. only the first one, we jump from the left, we jump to the right. But after that, you see the tangent that we are going to draw is closer and closer to the actual root from the right hand side. Alright, hence the next approximation is bigger. This is the root. This is the value for 2 to the power of 1 over 4 here. Okay, and you see that the approximate value of x which approach the value is from right hand side. So all these values are bigger than the actual root, right? Therefore, the next approximation is greater than 2 to the power of 1 over 4. Okay? So you see they can ask question like this. This one is a good example. Alright, one more. Let me see. One more question, one more examples. Like this. Okay, show that the equation 2 sine x equals x has a root between x1 and 2. Show. Use x equals 2 as a first approximation. Find by using Newton-Raphson method 2 more approximation to the root. Correct to 3 significant figure. They just want 2 more. Also to show the root, okay, remember, just calculate your f1, f2, opposite sign, one positive, one negative. Conclusion, since there is a change of sign, therefore the equation has a root between 1 and 2. So all this very common, right? Let the first approximation to, the question just now say, use Newton-Raphson method to find x2. So just sub into your formula. Don't forget to differentiate lah. Differentiate 2 sine x, you get 2 cos x. Differentiate x, you get 1. Alright, sub your 2 into the formula. Don't show this thing lah. Don't show the final answer. Okay, do like what we have done just now, like this one. You can see. Show this thing. Sub completely into the function. Okay, don't just show the final answer of f x1 and f prime x1. Alright, so you get the answer because they want 3 significant figures, right? So you see the example show 4 significant figures. Then sub these 4 significant figures into the Newton-Raphson method again. Alright, another 4 significant figures. So the question just want you to find 2 more approximations, so you can stop here. Alright, so to this is something extra actually. To illustrate a case where Newton-Raphson method fails. Okay, let the first approximation 1. Just now we choose 2, right? So how, you see, what happened if we choose 1? Okay, what happened if we choose 1? Okay, why we choose 2? You see, this is actually closer to 0, right? This is closer to 0 compared to this. Alright? Now, what happened if we choose 1? You see, if we choose 1, you see, f1, f prime 1. Okay, use second approximation. You see, the answer jump become -7 already. Just now the first approximate root is 1. This one, the second approximation, far away from the first root. Not like just this one. This one is close, very close. The x2, x1 is 2. This x2 is 1.9, close to 2. This one is closer again. Okay, not like this. The first approximation is 1. The next one jump to -7. Alright, so clearly this is absurd. Means it's failed. The failure of the method is due to the fact of the approximate x1 equals 1 is close to the root f prime x equals 0. Mean when x equals 1, the tangent at the curve is a line that very close to a horizontal line. It's because of this method. Alright, then this problem does not arise when x1 is 2. So let's go, it's something like this lah. It's something like this. The value that it choose may be here, which is very, very close to 0 already. Then when you draw the tangent, it's go far away. Alright? Okay. So these are 4 good examples lah, that you can refer again to your textbook and try to understand it. Alright? Okay. These are the host page. Okay, so remember, exercise 6.2, there are 13 questions there. Okay, please do it as your homework. Only one correction. Please do this correction. Question 8. Okay, this is x cubed minus 3x squared. Alright? Or else you cannot get the answer. Okay, this one will be your homework. Alright, so we have a rest for a while. Okay, then after that we continue another video where we are going to discuss all the past year questions related to Newton-Raphson method. Alright, okay, see you later.